Hi everyone, Nehorai here. Back with beautiful but lost algorithms, episode 2. And today we're gonna talk about the Nehorai and Porat algorithm from 1986. This is a spectral estimation algorithm, and spectral estimation algorithms are the cornerstone of lots of disciplines. So you find these applications in many disciplines, specifically my discipline, which is signal processing, statistical signal processing, and radar. You find a lot of spectral estimation type of needs or problems. It is common to observe a rich frequency domain. So, for example, cluttered with fundamental frequencies, their harmonies and intermodulations. For example, when I estimate breathing, when a radar is trying to extract breathing and heart rate simultaneously, the radar, being nonlinear inherently, is producing a rich type of spectrum in which you see the fundamental heart rate and its integer multiples like heart rate, 2 heart rate, 3 heart rates, and so on and so forth. Same for breathing, but you also see or observe their intermodulations, which is namely breathing frequency minus heart rate minus 2 heart rates, and so on and so forth. So you see a rich type of spectrum. The drawbacks of FFT are known. It suffers from lack of sufficient resolution unless you employ a large time windowing, which is sometimes just infeasible in a lot of applications. We will discuss the Nehorai and Porat algorithm from 1986, which is a novel adaptive filtering technique for the estimation and tracking of multiple frequencies. This is the paper. It's called the Adaptive Filtering for Harmonic Signal Enhancement. It's from 1986, and it's a very for any person who actually is doing some stuff with spectral estimation. This is a must to read paper. It's a very beautiful paper, and I was enjoying reading it. I read it more than one time. So what I will cover here is just the essence of the paper. Inside the paper you will see a lot of derivations. So they derive everything from this filtering approach to its Cramera all-over bound, in which you can benchmark against, and actually to the gradient, in which you can use for gradient descent optimization. Yeah, and we will see what I mean by that. So the model is given by Z of t equals Y of t plus W of t, where W of t is a white noise and Y of t is a combination or a superposition of sinusoids, with AK, F0, and phi k being unknown deterministic parameters, phi k and AK being nuisance parameters, and F0 is what we want to estimate. And you can see that we have all the integer multiple of F0 consisting in a spectrum, and the number of sinusoid is uppercase K. AK is assumed to be monotonically decreasing. So how do we efficiently estimate the fundamental frequency F0? So that's the Nehorai and Porat algorithm. They presented a stable IIR filter. So let's say, just for simplicity, that uppercase is 1. So we have just one harmony, and so lowercase k is 1. So we have this known term, which is 1 minus 2 cosine of omega 0 being 2 pi times f0. And we have the z, the filter in the z domain. And in the denominator, we have the row here, which is between 0 and 1, to establish stability of the filter. So this filter is a notch filter, if you will, a null filter that nulls out the frequency omega 0. It consists of 2k zeros on the unit circle and 2k poles inside the unit circle with radius ρ. Now, if we extend k to be more than 1, so we can see that we can null out, with this filter we can null out all the fundamental and all its integer multiples. That's how the filters look like. The filter is, so for example, this is a 3 harmony filter. It nulls out 0.3, 0.6, and 0.9 respectively. You can see the 6 poles, 6 zeros on the unit circle. That's how the filter looks like for k, for uppercase k equals 3. Raw in this case is actually 0.96. So the idea behind the filters, as we said, nulls out fundamental frequency and its integer multiples. Thus, we will take the filter's output as the error and try to minimize its energy. Thus, estimate the fundamental frequency. So if we put it formally, what we have here is, this is the inverse transform of the uppercase H, the filter. This is the convolution operation. So we pass Z, time domain sampled process through the filter, and we take the output and we basically calculate the power of the output, and we minimize over omega 0. Now the minimization optimization algorithm can be used or be executed using gradient descent or grid search over the frequency. The gradient is actually derived in closed form inside the paper, and one can use it for executing gradient descent iteration. Let's see how the filter looks like. So you can see here the null is actually moving as the filter updates its key coefficients. The poles and zero are moving. This is the adaptive type of operation of the filter. This is inside the gradient descent process, and you can see the filter tends to the true value. Sorry, the frequency estimation tends to the true value as we lower the cost and going through iterations of gradient descent. The Cremera all-over bound is something that we benchmark the estimator that we use. So this was derived by Nehorai and Porat to be given by this expression, where n is the number of samples, SNR is signal to noise ratio defined here. It's like an effective SNR taking into account all the amplitudes and the noise variance, and it's also comprised of the effective bandwidth, which is calculated here, and by definition it's basically the entire bandwidth of the frequency of the sinusoids, or sum of sinusoids. If we take the root mean square error of the estimator comparing against the Cremera all-over bound, the vertical axis being the root mean square error in hertz, and the horizontal axis being the SNR in dB, we can see that this, even in lower dBs, lower SNRs, the estimator is performing very nicely, very close to the bound. And as we go and increase the SNR, we get a what we call a efficient or asymptotically efficient estimator, which is very good for us. That's the reference, the Nehorai and Porat from 1986. If one wants to, Google it and download it from IEEE Explorer, it's available there. Very, very beautiful paper. I recommend everyone that is enjoying spectral estimation to read it. And that's my email address, near@aleph0.ai. If one wants to connect with me or email me some questions regarding this lecture or otherwise, feel free to do so. So again, thank you for attending and for your time watching the episode 2 of this program. I appreciate your time and I hope I added value to your knowledge. Thank you so much.